Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the fundamentals of programming. Today's topic is variables, data types, operators, and expressions. Over the next few slides, we'll dive into how these core concepts work together to create powerful and flexible programs. So, let's get started and see what's in store. Let's take a look at the contents of this section. Here, we'll cover key concepts like keywords and identifiers, constants, data transformation, and operators. These are fundamental building blocks in C programming. We'll explore relational operators, character sets, and data types, which help us understand how data is represented and manipulated. We'll also dive into how operators like arithmetic, logical, and bitwise work, along with their precedence and associativity, crucial for writing correct expressions. Shorthand assignment operators and special operators will be discussed to show more efficient coding techniques. Understanding rules for expression evaluation and order of evaluation will help us write predictable code. Throughout this presentation, connecting these topics will give us a clearer picture of how C handles data and operations internally, forming the foundation for writing effective programs. Let's take a look at the contents of this section. Here, we're covering the foundational elements of C programming, starting with character sets, which define the characters we can use in our code. Moving on, we have variables, which are essential for storing data during program execution. Then, we explore C tokens. These are the basic building blocks of the language, like keywords, identifiers, operators, and literals. Next, we'll discuss type conversions within expressions, which are important for understanding how data types interact during calculations. We also have implicit type conversions, where the compiler automatically converts types for us, and explicit type conversions, where we intentionally change data types using cast operators. We'll look into declaration and definition, which help us set up our variables and functions properly. Keywords and identifiers are fundamental for writing meaningful code, since keywords are reserved words, and identifiers are the names we choose. Constants are fixed values that don't change during execution, providing stability to our code. Operators and expressions are at the core of how we perform calculations and logic, so understanding them is crucial. Lastly, the slide touches on operator precedence and associativity, which determine the order in which parts of an expression are evaluated, ensuring our calculations are performed correctly. All these topics are interconnected and form the building blocks for writing efficient, reliable C programs. They also tie into the overall theme of understanding the core language structure to write better code. Let's take a closer look at the character set in C. When we talk about characters in C, we're referring to the basic data type used to store individual characters, like letters, digits, or symbols. This is typically represented by the char data type. It's important because it forms the foundation for handling text in C programming. The character set in C is based on the ASCII standard, which assigns a unique number to each character. For example, the letter A corresponds to the number 65, and the lowercase O is 97. This mapping allows us to perform operations like comparisons or conversions between characters and integers easily. Understanding the character set is crucial for tasks like input-output, string manipulation, and processing user data. It also helps us grasp how characters are stored and manipulated in memory, which is fundamental for writing efficient and effective C programs. So, in essence, the character set in C isn't just about individual characters. It's about understanding how these characters are represented, stored, and used within our programs to handle textual data seamlessly. Let's dive into the concept of character sets in C. When we talk about character sets, we're referring to the collection of characters that a program can recognize and work with. In C, this is crucial because it defines how data like text is represented and manipulated. The most common character set is ASCII, which includes 128 characters such as letters, digits, and some special symbols. But modern C programs often use extended sets like Unicode to support a wider range of characters from different languages. Understanding character sets helps us write more portable and robust code. It ensures that the characters we use are correctly interpreted across different systems. This ties into the overall theme of writing efficient and compatible C programs, as handling characters properly is fundamental to applications like text processing, user interfaces, and data input. So, grasping these concepts about character sets is a key step in mastering C programming and building versatile software. Let's talk about 1.3C tokens. These are the smallest individual units in language processing, and we call them tokens. Think of tokens as the building blocks of text. They can be words, parts of words, or even characters. Understanding tokens is crucial because they form the foundation for how models interpret and generate language. By breaking down text into tokens, models can analyze and predict language more effectively. This concept ties directly into the overall theme of how AI understands and works with language at a granular level. So, recognizing these tiny units helps us appreciate the complexity and precision behind natural language processing. Now, let's talk about keywords and identifiers in C. Every C word falls into one of these two categories. It's important to understand the difference because it impacts how we write and interpret code. Keywords are special reserved words that have a fixed meaning in the language. Their purpose is well defined, and this meaning cannot be changed. Think of them as the building blocks for creating program statements. They form the core syntax of the language. Also, you'll notice that keywords must be written in all lowercase letters. This helps distinguish them from identifiers, which are names we choose ourselves, like variable names or function names. Recognizing these keywords and understanding their fixed roles is fundamental as we start to write and analyze C programs. Let's talk about keywords and identifiers. Identifiers are essentially the names we give to variables, functions, and arrays in our code. They are fundamental because they help us refer to different elements in a clear way. Now, there are some important rules to keep in mind when choosing identifiers. First, the very first character must be an alphabet or an underscore. This helps the compiler recognize it as a valid name. Second, identifiers can only contain letters, digits, or underscores, not spaces or special characters. It's also good to note that only the first 31 characters are considered significant, so longer names won't add any uniqueness beyond that limit. Another key point is that identifiers cannot be the same as a keyword. Keywords are reserved words in the programming language, and using them as identifiers would cause confusion or errors. Finally, identifiers must not contain white spaces, which makes sense because spaces are used to separate different elements in code. Understanding these rules helps us write clean, error-free code and ensures that our identifiers are valid and meaningful within the overall structure of our program. All right, let's talk about constants in C. Basically, constants are fixed values that we define in our programs, and they don't change as the program runs. This is really useful because it helps us avoid accidental modifications to values that are meant to stay the same, like pi or the maximum size of an array. When we declare a constant, we're essentially telling the compiler, hey, this value is constant and shouldn't be altered. This makes our code safer and more readable. Connecting this to the overall theme, understanding constants is fundamental because it reinforces good coding practices, making our programs more reliable and easier to maintain. Now, let's take a closer look at integer constants and how they can be represented in exponential format. When we talk about this format, it's typically written as the mantissa, followed by the letter E, and then the exponent. The mantissa can be either a real number in decimal notation or just an integer. This gives us some flexibility depending on the precision or the size of the number we're working with. The exponent itself is always an integer, and it can include an optional plus or minus sign, which indicates whether we're moving the decimal point to the right or left. And a quick note, the letter E can be written in lowercase or uppercase, so both are acceptable and commonly used in programming or mathematical notation. This exponential form is particularly useful for representing very large or very small integers efficiently, especially in contexts like scientific calculations or programming where handling such numbers precisely is important. Understanding this format helps us connect how constants are represented in code and in mathematical expressions, tying into the broader theme of how data types and numeric representations work behind the scenes. Let's talk about constants in programming, specifically on slide 11. When we refer to constants, we're talking about fixed values that don't change during program execution. This includes single character constants, string constants, and backslash character constants. These backslash sequences are particularly useful in output functions because they help us format output in specific ways. For example, escape sequences are used to insert special characters like newlines or tabs into strings. They're called escape sequences because the backslash escapes from the normal flow and introduces a special character. Understanding these constants and escape sequences is key to manipulating output precisely and making our programs more flexible and readable. So, in the context of our overall theme, mastering these constants allows us to have better control over how data is represented and displayed, which is fundamental in effective programming. Let's talk about escape sequences. These are special characters we use in programming to represent characters that are difficult to include directly in strings. For example, if we want to insert a new line, a tab, or even include quotes inside a string, we use escape sequences. They usually start with a backslash, which is the escape character itself. So for a new line, we write backslash followed by an N, and for a tab, it's backslash followed by T. Understanding and correctly using escape sequences is crucial because they help us control how our strings are formatted and displayed. They connect to the overall theme by showing how we can manipulate text output effectively in programming. This small but powerful concept ensures that our code can produce clear, readable, and well-formatted text. Let's talk about variables. A variable is essentially a data name used to store data values, and what's important is that it can hold different values at different times during the execution of a program. It's like a container that can change what it holds as your program runs. When working with variables, there are some important rules to keep in mind. First, a variable should not be a keyword, because keywords are reserved words in the programming language with specific meanings. Also, your variable name should not contain any white space, so no spaces in the name. Another key point is that uppercase and lowercase letters are significant, meaning that variable and variable are considered different names. Variables must begin with a letter or an underscore, which helps keep things clear and consistent. Lastly, it's generally recommended to keep variable names to no more than about 8 characters for simplicity and readability. Understanding these rules helps ensure your variables are valid and your code is easy to understand and maintain. Remember, choosing clear, valid variable names is a foundational step in writing effective programs. Let's talk about data transformation. Essentially, programs are designed to convert data from one form to another. For example, input data becomes output data, and a stimulus triggers a response. This process is fundamental because it's how programs make sense of and manipulate information. Now, since programming languages store and process data in different ways depending on the data type, it's crucial that all data read, processed, or written has a specific type. Think of data types as categories that tell your program what kind of data it's dealing with, like numbers, text, or dates. 2 key characteristics of any programming language are, first, the data types it supports, and second, the operations that can be performed on those data types. These features define what kind of data you can work with and what you can do with it. By understanding these concepts, we see how the way data is handled influences the design and functionality of programs, tying back to the overall theme of how programming languages enable effective data processing. Let's take a closer look at data types in C. C is quite rich in its data type options, which is a big advantage for programmers. Having a variety of data types means you can choose the most appropriate one depending on what your program needs to do. This flexibility helps optimize memory usage and processing efficiency. Now, specifically, ANSI C supports 3 main classes of data types. First, we have the primary or fundamental data types. These are the basic building blocks like int, float, char, and so on, which form the core of data handling. Next, there's the derived data type. These are types that are built from the fundamental types, such as arrays, pointers, and structures. They help organize and manage data more effectively in complex programs. Finally, there's the user-defined data type. This is where you, as a programmer, can create your own data types tailored to your specific needs, enhancing code readability and reusability. Understanding these classes of data types is crucial because it ties directly into writing efficient, clear, and effective C programs. It's all about giving you the right tools to handle data appropriately in different situations. Let's take a closer look at data types in C and programming. Understanding data types is crucial because they define the kind of data a variable can hold. In C, there are several fundamental data types, each serving a different purpose. For example, integers are used for whole numbers, and they come in various sizes like short, int, and long, depending on the range of values you need. Then, we have floating point types such as float and double, which are used to represent real numbers with decimal points. Char is another important data type, representing individual characters like letters or symbols. Recognizing these types helps us manage memory efficiently and write more effective code. Throughout this course, we'll see how choosing the right data type impacts the performance and correctness of our programs. So, understanding these core data types sets the foundation for everything else we'll explore in C programming. Let's take a closer look at data types. In C, this slide highlights the fundamental building blocks of any program, the data types. In C, understanding data types is crucial because they determine what kind of data we can store and how much space it will occupy in memory. For example, we have basic data types like int for integers, float for decimal numbers, and char for characters. Each of these serves a specific purpose and helps us write efficient and effective code. Recognizing the right data type for a given situation not only improves performance, but also makes the code more readable and maintainable. As we proceed, keep in mind that mastering data types is essential because they form the foundation for more complex programming concepts. Let's take a closer look at expressions, which are essentially the combination of operators and operands. Think of expressions as the building blocks of programming logic. For example, consider the expression 2y plus 5. Here, the numbers and variables like 2, y, and 5 are the operands, while the symbols like and plus are the operators. Operators are the actions we perform, such as multiplication or addition, and operands are the values or variables we work with. Together, they form expressions that tell the program what calculations or evaluations to perform. Understanding how operators and operands work together is fundamental because they are the key elements that make expressions meaningful and functional in programming. This concept ties directly into the overall theme of how programming languages process and evaluate data to produce results. All right, let's talk about what an operator is. An operator is essentially a symbol like plus, minus, multiply, or divide. So, plus, asterisk, that tells the computer to perform a specific mathematical or logical operation. These operators are fundamental because they help us manipulate data and variables within our programs. For example, if I have an expression like a plus b, the plus sign is the operator that instructs the computer to add the values of a and b together. Recognizing these operators and understanding how they work is crucial because they form the building blocks for more complex calculations and decision-making in programming. So, in essence, operators are the commands that direct the computer on what kind of manipulation to perform on data. Let's take a closer look at the operators in C. These are essential tools that allow us to perform various operations within our programs. First up are the arithmetic operators, which include addition, subtraction, multiplication, division, and modulus. These are fundamental for calculations. Next are the assignment operators, used to assign values to variables, with the equals sign being the most common. Then we have bitwise operators, which work at the bit level and are useful for low-level programming tasks. Relational operators are used to compare values, such as equal to, not equal to, greater than, and less than, forming the basis of decision-making in code. We also have increment and decrement operators, which increase or decrease a variable's value by 1. These are handy in loops and iterative processes. Special operators include things like sizeoff and comma, which serve specific purposes in certain contexts. Moving on, logical operators, such as and, or, and not, help us combine or negate conditions, making our decision structures more robust. Conditional operators, often called ternary operators, allow us to choose between two values based on a condition in a concise way. All these operators play a vital role in making our C programs powerful and flexible, allowing us to manipulate data and control program flow effectively. Understanding these operators is key to mastering C programming and building efficient, effective applications. Let's take a closer look at some common arithmetic operators. On this slide, we have a table that breaks down the basic symbols, their examples, and what they mean. First, we see the plus sign, which stands for addition. For example, a plus b means we're adding two values together. Interestingly, addition can also be unary, which means it can operate on just one operand, like plus a, though that's less common. Next, we have the minus sign. A b represents subtraction, and similar to addition, it can also be unary, as in a, which simply negates the value. Moving on, the asterisk symbolizes multiplication. So, a asterisk b is multiplying two numbers. Then there's the forward slash, which indicates division. A slash b divides one number by another. Finally, we see the percent sign, which is used for modulo division. This operator gives us the remainder after division. For example, a percent b will tell us what's left over when a is divided by b. Understanding these operators is fundamental because they form the backbone of most calculations in programming. They allow us to perform a wide range of mathematical operations, and recognizing their symbols and meanings helps us write clearer, more effective code. This sets the stage for more complex expressions and algorithms we'll explore later in the presentation. All right, let's take a closer look at some common relational operators that you'll frequently encounter in programming. These operators are fundamental because they allow us to compare values and make decisions based on those comparisons. First up is the less than operator, which is represented by the symbol. When we use this, we're checking if one value is smaller than another. For example, if we want to see if age is less than 18, we'd write age 18. Next, we have less than or equal to, written as less or equal. This operator checks if a value is either smaller than or exactly equal to another. It's useful when we want to include the boundary condition in our comparisons. Moving on, there's the greater than operator, which, as you might guess, tests if one value exceeds another. For instance, score 50 checks if someone scored more than 50 points. Then there's greater than or equal to, represented as greater or equal. This is similar to the previous one but includes equality, so it checks if a value is at least a certain amount. Now, for equality, we use equals equals. This is crucial because it allows us to test if two values are exactly the same. For example, if user input equals 10, we're confirming if the input is exactly 10. Finally, there's the not equal to operator, which is equals. This checks if two values are different. For example, if code equals 0, we're ensuring that the code isn't 0. These operators form the backbone of decision-making in programming, enabling us to write conditions and control the flow of our programs. Remember, understanding these will help you create more dynamic and responsive code. Let's take a closer look at logical operators, which play a crucial role in building complex conditional statements. On this slide, we see two key operators. First, the and operator, which stands for logical and. This means that for the entire expression to be true, both conditions connected by and must be true. Then we have the operator, which is the logical not. It's used to reverse the truth value of a condition. If something is true, applying makes it false and vice versa. Now, when we talk about logical expressions or compound relational expressions, we're essentially combining multiple relational expressions to form more complex conditions. For example, if you want to check if variable A equals B, and at the same time, B equals C, you can write if A equals B and B equals. Here, both conditions need to be true for the overall expression to evaluate as true. Understanding how these operators work together allows us to create more nuanced decision-making in our programs, which ties back to the overall theme of controlling program flow effectively. So, mastering these logical operators is fundamental for writing precise and efficient conditional statements. Let's take a closer look at this truth table. Here, we're examining the expression A and B, which is a logical AND operation, alongside the value of the expression itself. As you can see, when both A and B are 0, the result is 0. If A is 0 and B is 1, the result is 1. Similarly, if A is 1 and B is 0, the result is again 1. And finally, when both A and B are 1, the result is 1 as well. What's interesting here is how the AND operation behaves. It only yields a true or 1 result when both inputs are true or 1. This pattern is fundamental in logic because it helps us understand how different conditions combine. This table is called a truth table, and in this case, it's specifically the 1.22 truth table, illustrating exactly how the AND operator works across all possible input combinations. Understanding this is crucial because it ties directly into how complex logical expressions are built up from simple operations. So, as we move forward, keep in mind how these basic truth tables form the building blocks for more advanced logical reasoning and programming logic. Let's take a look at assignment operators, which are a crucial part of coding. The basic syntax is straightforward. VOP equals exp, where V is your variable, op is the shorthand assignment operator, and exp is the expression you're assigning. For example, instead of writing x equals x plus 3, you can simply write plus equals 3. This shorthand makes your code cleaner and more efficient. Remember, these operators help you modify variables quickly without rewriting the entire expression each time. They're all about streamlining your code and making it more readable. So, understanding these operators is essential as we progress, because they'll come up frequently in our coding exercises and real-world programming tasks. Let's take a closer look at some common assignment operators and their shorthand versions. As you can see in the table, the simple assignment operator is the equals sign, like A equals a plus 1, which is written as A equals a plus 1. The shorthand operator for this is a plus equals 1, making the code more concise and easier to read. The same idea applies to subtraction, where a 1 can be shortened to A equals 1. For multiplication, instead of writing A equals a asterisk, m plus n, you can simply write A asterisk equals m plus n similarly. For division, a slash m plus n becomes a slash equals m plus n, and for the modulus operation, A equals a percent b turns into a percent equals b. These shorthand operators are very useful because they help us write cleaner, more efficient code. They also make it easier to understand the operations being performed, especially when working with complex expressions. Remember, these operators are a key part of writing more concise code, which is essential as we develop more advanced programming skills. Now, let's move on to the 1.25 increment and decrement operators in C. C supports two very useful operators that help us manipulate values easily. First, there's the increment operator, which is written as plus plus. This operator adds 1 to the operand, so if you have a variable A writing plus plus, or a plus plus will increase its value by 1. It's important to note that the position of the plus plus matters, especially when you're using it in expressions, because it can either increment before or after the value is used. Next, there's the decrement operator, written as. This one subtracts 1 from the operand, functioning just like the increment, but in reverse. Again, you can write O or A, with similar considerations about timing depending on where you place it in your expression. These operators are fundamental for loops and iterative processes, making your code cleaner and more efficient. By understanding how and when to use them, you gain more control over your program's flow and logic. Let's take a closer look at the rules for the plus plus and operators. First, it's important to remember that these operators require variables as their operands. You can't just apply them to literals or constants. Now, when we use the postfix form, which is either plus plus or after the variable, the key thing to note is that the expression is evaluated first. Only after the expression has been evaluated does the variable get incremented or decremented by 1. This means that if you use x plus plus, the current value of x is used in the expression, and then increases by 1 afterward. On the other hand, if you use the prefix form, like plus plus x or x, the variable is incremented or decremented by 1 first, and then the expression is evaluated with this new value. So, in this case, the change happens before the value is used in the expression. Understanding these differences is crucial because it affects how your code behaves, especially in more complex expressions. Recognizing whether you want the variable to change before or after the expression is evaluated helps you write clearer, more predictable code. This ties back to our overall theme of mastering operators to write efficient and accurate programs. Let's look at some examples of the plus plus and operators in action. Suppose we start with a equals 5. If we write b equals plus plus a, what happens? Well, the plus plus before a means we increment a first, so it becomes 6, and then b gets that value. So after this operation, both a and b are 6. Now consider if we start again with a equals 5, but this time we write b equals a plus plus. Here, the plus plus after a means we use the current value of a for b, which is 5, and then increment a afterward. So a becomes 6, but b remains 5. This highlights a crucial difference. The placement of the plus plus operator determines whether the increment happens before or after the value is assigned. It's a subtle point, but understanding it is key to controlling how your variables change during execution. These examples tie back to our overall theme of understanding operator behavior in programming, helping us write more predictable and error-free code. Let's talk about the difference between prefix and postfix operators. With a prefix operator, the key point is that it first adds 1 to the operand, and only after that does it assign the new value to the variable on the left. This means the increment happens before any other operation involving that value. On the other hand, with a postfix operator, the process is slightly different. It first assigns the current value to the variable, and only afterward does it increment the operand. So, the increment happens after the value has been used or assigned. Understanding this distinction is crucial because it affects the order of operations in your code, which can lead to different results depending on which form you use. It's a fundamental concept that ties into how expressions are evaluated and how your program's logic flows. Let's take a closer look at the conditional operator, which is often called the ternary operator because it involves 3 parts. The syntax looks like this: exp1, exp2, exp3. Here, exp1, exp2, and exp3 are all expressions. The way it works is pretty straightforward. First, exp1 is evaluated. If exp1 evaluates to a non-zero value, which we interpret as true, then exp2 is evaluated, and its value becomes the value of the entire expression. On the other hand, if exp1 is 0, meaning false, then exp3 is evaluated, and its value becomes the result. To make this clearer, let's look at an example. Suppose we have 2 variables, m equal to 2 and n equal to 3. We want to assign the larger of the 2 to a variable r using the ternary operator. We write r equals mn. mn. In this case, mn evaluates to false because 2 is not greater than 3. So, the expression after the colon, which is n, gets assigned to r. This compact form is very useful because it allows us to make decisions and assign values in a single line, keeping our code clean and efficient. So, the key takeaway here is that the conditional operator is a concise way to perform simple if-else logic, especially useful for assignments based on conditions. Now, let's take a closer look at some bitwise operators. These are powerful tools that allow us to manipulate data at the bit level, which is essential for low-level programming and optimizing performance. First up is the ampersand symbol, which represents the bitwise AND. When we use this operator, it compares each bit of two values and returns a 1 only if both bits are 1. Think of it as a way to filter bits, keeping only the bits that are set in both values. Next is the caret symbol, which stands for bitwise exclusive OR, or XOR. This operator compares bits and returns a 1 only when the bits are different. It's really useful for toggling bits or performing certain encryption tasks. Then we have the shift operators. The double less than symbol shifts bits to the left. This effectively multiplies the number by 2 for each shift position, which can be handy for quick calculations. Similarly, the double greater than symbol shifts bits to the right. This divides the number by 2 for each shift, discarding bits as needed. It's a fast way to perform division by powers of 2. Overall, these bitwise operators give us fine-grained control over data, enabling efficient manipulation at the binary level. They are a cornerstone in systems programming, embedded development, and when performance is critical. Understanding how these operators work helps us write more optimized and effective code, fitting perfectly into our broader theme of mastering data manipulation techniques. Let's take a look at some of the special operators in C++. First up is the comma operator, which allows us to separate multiple expressions where only one is expected, and it returns the value of the last expression. It's quite handy in certain situations. Next, we have the pointer operators, which are the ampersand and the asterisk. The ampersand is used to get the address of a variable, essentially creating a pointer to it, while the asterisk dereferences a pointer, giving us access to the value stored at that address. Understanding these is crucial when working with dynamic memory and pointers. Then there's the sizeof operator. This is a compile-time operator that tells us the size, in bytes, of a data type or a variable. It's very useful for memory management and ensuring portability across different systems. Finally, we have the member selection operators, which include the dot operator and the arrow operator. The dot operator is used to access members of a structure or class when you have an object, while the arrow operator is used when you have a pointer to a structure or class to access its members directly. All of these operators play a vital role in writing efficient, clear, and effective C++ code, especially as we work more closely with memory management and data structures. Let's take a closer look at this table to understand the relationship between algebraic expressions and their corresponding C expressions. For example, the expression a times b minus c in algebra translates directly to a asterisk b c in C. It's straightforward. Multiplication is denoted by an asterisk, and subtraction remains as minus. Similarly, when we see m plus n multiplied by x plus y, the C equivalent is simply m plus n, x plus y. The key point here is that the structure of the algebraic expression is preserved, but the operators are explicitly written out in C. Now, consider more complex expressions, like a asterisk b divided by c. In algebra, it's written as a asterisk b slash c, which is directly mirrored in C syntax. Another example is a quadratic term, 3x2 plus 2x plus 1, which in C becomes 3 asterisk x plus 2 asterisk x plus 1. Notice how we explicitly write the multiplication with an asterisk, especially for powers or repeated variables. Finally, there's the expression for S, which is the sum of a b and c divided by 2, written as S equals a plus b plus c slash 2. This highlights how division and grouping are handled consistently in C. Overall, understanding these mappings helps us translate algebraic formulas into C code accurately, maintaining their mathematical meaning while adapting to programming syntax. Now, let's take a closer look at this table, comparing algebraic expressions with their C language equivalents. First, we see the expression for the area of a triangle using Heron's formula. The algebraic form is simply area equals, and in C, it translates to area equals sqrt, ss of sb, sc. Next, there's an expression involving the sine function. The algebraic version is sin B/SQRT, A plus B, which calculates the sign of a ratio involving side lengths. Moving on, there's a slightly more complex expression for TO1. In algebra, it's written as TO1 equals SQRT, Rox ρe slash 2 plus TO y asterisk y. Notice that in C, we need to be precise with the order of operations, so it's written as TO1 equals SQRT, POW, Rox ρe slash 2 plus TO y asterisk y. Finally, there's an expression for y involving angles and absolute values. Y equals alpha plus beta, sin, theta 3.1416/180 plus abs, x. Here, we're converting degrees to radians for the sine function and adding the absolute value of x. Now, let's connect this to our broader theme. These examples highlight how algebraic expressions translate directly into C code, emphasizing the importance of understanding both the math and syntax to implement formulas correctly. And remember, when working with functions like sine, always convert degrees to radians to ensure accurate calculations. Let's talk about the precedence of operators, which is crucial for understanding how expressions are evaluated in programming. The BODMAS rule is a helpful way to remember the order: brackets, division, multiplication, addition, subtraction. Essentially, brackets always take the highest priority and need to be evaluated first. Once that's done, division and multiplication come next, followed by addition and subtraction. In C language, this concept is reflected through what we call precedence rules or the hierarchy of operations. Not all operators are equal in priority. Some have higher precedence than others. For example, multiplication, division, and modulus operators, which are asterisk, slash, and percent, have the highest priority. On the other hand, addition and subtraction, represented by plus and have lower priority. Understanding these precedence levels helps us predict how complex expressions will be evaluated without confusion. It ensures that operations are performed in the correct order, which is essential for writing reliable and predictable code. Remember, the key takeaway here is that operators like asterisk, slash, and percent are evaluated before plus and. This hierarchy is what allows us to write expressions that the compiler can interpret correctly, keeping our programs functioning as intended. Let's go through some key rules for evaluating expressions. First, when we encounter parentheses, we evaluate the subexpressions inside them from left to right. This means that the innermost parentheses are tackled first, which is crucial for understanding the order of operations. Speaking of order, the precedence rule guides us in determining which operators to evaluate first when multiple operators are present. It ensures that multiplication and division, for example, are performed before addition and subtraction, unless parentheses tell us otherwise. Next, when we evaluate arithmetic expressions, we generally go from left to right, but we always keep the precedence rules in mind to maintain the correct order. If parentheses are nested within each other, we start evaluating from the innermost set and work our way outward, ensuring that each level is handled systematically. The associativity rule also comes into play when we have two or more operators of the same precedence level in a subexpression. This rule helps us decide whether to evaluate from left to right or right to left, depending on the operator. Finally, whenever parentheses are used, the expressions within them are given the highest priority. This overrides other rules, making sure that what's inside those parentheses is evaluated first. All these rules work together to make sure we evaluate expressions correctly and consistently, which is essential for understanding how calculations are performed in programming and mathematics. All right, let's take a closer look at this table. It outlines the hierarchy of operators, which is crucial for understanding how expressions are evaluated in programming. Starting with the first row, we see parentheses and brackets. These are used for function calls and array element references. The key thing here is that they have the highest precedence and are evaluated from left to right. So, when you see an expression with parentheses, it means whatever's inside gets evaluated first. Moving down, the second row involves unary operators like plus, minus, increment, decrement, logical negation, and the one's complement. as well as pointer reference and address operators. These are evaluated from right to left, which is somewhat unique. For example, when you have multiple unary operators, the order in which they are applied matters, and they are processed in reverse order compared to binary operators. Next, we have multiplication, division, and modulus operators. These fall under the left-to-right evaluation, meaning if you have an expression with multiple of these, they are evaluated from left to right, respecting their precedence. Understanding this hierarchy is fundamental because it influences how complex expressions are interpreted and executed. Recognizing which operators bind more tightly helps avoid bugs and makes your code clearer. Overall, this hierarchy ties into the broader theme of understanding language syntax and semantics, ensuring you write precise and predictable code. All right, let's walk through example 1. Here, we're evaluating the quadratic formula for x1, which is given by plus the square root of bb minus 4ac, all over 2a. So plugging in our values, a equals 1, b equals minus 5, and c equals 6. When we substitute these in, we get x1 equals minus 5, plus the square root of minus 5 times minus 5, minus 4 times 1 times 6, all over 2 times 1. Notice how minus 5 simplifies to 5. Then, inside the square root, we have 25 minus 24, which simplifies to 1. Next, taking the square root of 1 gives us 1. So now our numerator is 5 plus 1, which totals 6. And the denominator is 2 times 1, which is 2. Finally, dividing 6 by 2 gives us 3. So the value for x1 in this case is 3. It's important to recognize how this process demonstrates the application of the quadratic formula, especially the handling of the square root part, which determines the nature of the roots. This example helps reinforce the key idea that by carefully substituting and simplifying step by step, we can accurately find the roots of a quadratic equation. All right, let's look at this example to see how the evaluation works when we modify the value of a during the calculation. So, we start with a equals 4. Now, b is assigned the value of a minus the pre-increment of a, which is plus plus of this means that before we do the subtraction, a is increased by 1, so it becomes 5. Then, b is calculated as a minus this new value of a, which is 5. So b equals 5 minus 5, resulting in 0. The key point here is understanding the difference between pre-increment and post-increment. In this case, pre-increment plus plus, a increases a before it's used in the expression. This example also highlights how the order of operations affects the final result. When evaluating expressions involving increments, it's crucial to keep track of how and when the variables change. Overall, this ties back to our main theme, understanding operator precedence and side effects in expressions. It's important because these details can significantly impact the outcome of our code. Now, let's take a closer look at the order of evaluation in C++, which is crucial for understanding how expressions are processed. At the very top, we have the highest precedence, which includes parentheses and array subscripting, as well as the arrow operator. These are evaluated first because they define the most immediate operations. Next, we have the unary operators like the logical not, bitwise NOT, increment, decrement, dereference, and addressive operators. These come right after parentheses in the priority list. Following that are unary plus and minus, which are straightforward but still important for expression evaluation. Moving down, we reach the multiplicative operators, multiplication, division, and modulus, with a precedence level of 4. These are evaluated before additive operators, which include plus and minus, at level 5. Then, we encounter the relational operators such as equal to, not equal to, less than or equal to, greater than and greater than or equal to. These are evaluated after the additive operators. The bitwise XOR operator comes next, with a precedence level of 3, which might seem a bit unusual since it's lower than relational operators. At a higher level, we have the bitwise AND, followed by the bitwise OR, and then the logical AND and OR operators, which are critical for combining Boolean expressions. The logical AND takes precedence over the logical OR, and both are evaluated before assignment operators like equals, plus equals, and so on. Assignment operators themselves come at a lower precedence, meaning that in an expression, calculations are performed first, and then the results are assigned. Lastly, the comma operator, which allows for sequencing expressions, has the lowest precedence of all. Understanding this hierarchy helps us predict how complex expressions will be evaluated, ensuring our code behaves as expected. Always keep these precedence rules in mind to write clear and bug-free code. Let's talk about type conversions in expressions, specifically implicit type conversion. In C, you can mix constants and variables of different types within an expression without any fuss. The language handles this automatically by converting intermediate values to the appropriate type so that the expression evaluates correctly. This process is what we call implicit type conversion. Now, a key rule to remember is that the lower type is always automatically converted to the higher type. For example, if you're combining an int and a float, the int will be promoted to a float before the operation proceeds. This ensures that no significant data is lost during the calculation. Understanding this automatic conversion is crucial because it helps us write safer, more predictable code. It also connects to the overall theme of how C manages data types efficiently behind the scenes, making complex expressions work seamlessly. Let's look at this example to understand type conversions better. We start with declaring some variables, int I and x, then double D, float f, and long int li. The key point here is that when we perform an assignment, the final result of an expression is converted to the type of the variable on the left side of the assignment. So, for instance, if we assign a double value to an int variable, the value is converted, often losing the fractional part. This highlights the importance of being aware of implicit conversions to avoid unexpected results. Remember, understanding these conversions helps us write more predictable and reliable code, especially when working with different data types together. Let's talk about operator precedence and associativity. These are crucial rules that determine how expressions are evaluated in programming. First, precedence rules decide the order in which different types of operators are applied. So, for example, multiplication happens before addition. Then, associativity rules come into play when we have multiple operators of the same precedence level. They tell us whether to evaluate from left to right or right to left. For instance, in an expression like a equals I plus 1 equals jk, and in 3 equals x, understanding these rules helps us figure out the exact order of evaluation. And if you want a quick summary of how C operators are prioritized, you can refer to Table 3.8 on page 71. Remember, grasping these rules is key to understanding how complex expressions are processed in programming.